In part D of the theorem above, we were using the fact that the limit as z goes to z0 of g of z is equal to wg, which in turn means that we can make g of z minus wg less than any number epsilon prime in modulus here. And then we wanted to rearrange this inequality to say that this means that g of z is bigger than wg minus epsilon prime. And the way we do that is using the reverse triangle inequality, which is shown here. The modulus of z2 minus z1 is bigger than or equal to the difference of the moduli, the modulus of z2 minus the modulus of z1. So we're going to make this one our z1 and this one our z2, and we're going to need to use the fact that the modulus of z2 minus z1 is equal to the modulus of z1 minus z2. These two complex numbers are just negatives of one another, and so they'll have the same modulus. A plus bi and a negative a minus bi have the same modulus. The minuses get squared, and so they disappear. All right, so we have epsilon prime is bigger than g of z minus wg in modulus. And now we'll just switch the order of these two. Wg minus g of z in modulus. And now we will apply the reverse triangle inequality. So this is, we have the modulus of a difference, that's the left side here, is bigger than or equal to the difference of the moduli. So bigger than the modulus of wg minus the modulus of g of z. Let's just rewrite this. Epsilon prime is bigger than wg minus modulus g of z. And now we will write the modulus of g of z on the left and move the epsilon prime to the right, and we will get exactly this. The modulus of g of z, adding it to both sides, is bigger than the modulus of wg, and then subtract epsilon from both sides, epsilon prime, and there it is. So in that proof of part D, we were assuming this because this limit was given, and then we can turn this inequality into this one using the reverse triangle inequality.